Hello, today I want to talk about mirror image symmetry from different viewpoints. We are very used to mirror image symmetry. We see it in games, we see it in sports, we see it in art, in architecture, and it's even said that people are attracted to other people according to the symmetry of their face. But there are also a lot of objects that don't have mirror image symmetry that we encounter. One of the most annoying ones for students is desks which are right-handed if the student is left-handed. So often a classroom is filled with mostly right-handed desks and a few left-handed ones, and for a left-handed student to have to take notes on a right-handed desk is very challenging and annoying. So this is a good example of the fact that asymmetric objects, like people who favor one hand, react differently with other asymmetric objects, like desks that are either left-handed or right-handed. On the other hand, if we think about a symmetric object, like a piece of paper, it'll react the same way whether it's put on top of a left-handed desk or a right-handed desk. And this is also typical of what happens when symmetric objects react with asymmetric objects. An important example of where symmetry and asymmetry play a role is with pharmaceutical products. For example, if we consider the anti-inflammatory medication ibuprofen, one of its forms is what helps your headache or your cramps or your joint pains, and the other form is inert. It just passes through your body and has no effect on you. On the other hand, another anti-inflammatory medication, naproxen, one form of it helps your joint pain or your headache. The other form is toxic and could actually kill you. So when pharmaceutical companies make the medication, they have to separate out the bad one to make sure you're only having the good form of the medication. A third example is an old-fashioned painkiller which is called Darvon, and its mirror image is actually a cough suppressant, which is called Navrad. And what's funny is if you look at the word Darvon, D-A-R-V-O-N, and you look at the word Navrad, N-O-V-R-A-D, you see that the words are mirror images of each other. So even the pharmaceutical company who makes it has a sense of humor. Normally, when drugs are synthesized, they come in a 50-50 mix of the two mirror image forms. If a molecule has mirror image symmetry, they're exactly the same. But if a molecule doesn't, then the pharmaceutical company may have to actually separate out the two forms in case one of the forms has bad side effects or could even be toxic. This is expensive, and pharmaceutical companies would rather not have to do this. So they actually would prefer molecules that have mirror image symmetry. But what do we mean by mirror image symmetry? There's the easy answer that we think of immediately, which is something has mirror image symmetry if, as a rigid object, like a desk in a classroom, it's identical to its mirror image form. But not all objects are rigid. An example is a crumpled up sock. If we look at a crumpled up sock in the mirror, it will be different from the one I'm holding in my hand. But what's important is that when I straighten out the sock, it's exactly the same as its mirror image, and that's what my feet care about. My feet are asymmetric, they're different from one another, but they react the same way to a sock because a sock is actually symmetric. So even if it looks like it's asymmetric, because it's flexible, what's important is that it relates to my 2 feet the same way. The same is true for medications. It's not so much what they look like that matters, it's how our bodies react to them. And so pharmaceutical companies care more about the behavior of the molecule than its actual form and how it looks. For this reason, we introduced the definition as follows, that a molecule is chemically chiral if it cannot transform itself into its mirror image. And otherwise, we say it's chemically achiral. Now, this definition is very confusing to remember because we're used to words like political and apolitical, where political means you care about politics, and apolitical means you don't care about politics. But here it seems to be backwards. because it's chemically chiral if it cannot transform itself to its mirror image, and it's chemically achiral if it can transform itself to its mirror image. So how are we going to remember these two different words? And the good way to remember it is to think about the etymology of the word. So the word chiral comes from the ancient Greek word that means hand. So a left hand and a right hand are mirror images of each other, and my right hand can't turn into my left hand no matter what I do. So when I say a molecule is chemically chiral, I mean it's just like a hand. And when I say it's chemically achiral, I mean it's not like a hand. So indeed, chiral is the positive condition of being like a hand, where achiral is the negative condition of being not like a hand. So you should try to remember that for the rest of the talk because it will be important. The problem here is that when a pharmaceutical company is synthesizing a new medication, they want to know before they synthesize it whether it will be the same or different from its mirror image. And that means they want a definition that they can use to tell whether a model of the molecule will be the same or different from its mirror image. So even though chirality has to do with the behavior of the molecule, they'd like to be able to predict that behavior a little bit before they synthesize it. And so for that reason, we introduce a definition that depends on geometry. So you may remember from high school when you took geometry that geometry is the study of rigid shapes. And so we're going to say that an object is geometrically chiral, remembering that chiral is like a hand, if it cannot be rigidly superimposed on its mirror image. In other words, like a hand, it's different from its mirror image. And otherwise, we say an object is geometrically achiral. That is, as a rigid geometric object, it's the same as its mirror image. An example of this is the molecule I'm showing you on the screen. Now, when you look at this molecule, you might not understand what the lines mean. And I have a model here to help us look at it. And what we see is that the straight little segments in the screen mean that those bonds are actually just in the plane of the screen. So here we have this bond going from the central C to the top CH3, which I have a green ball that represents that, is just in the screen, as is this bond going from the C to the H. On the other hand, this bond that's a little purple triangle, you're supposed to view that as coming in front of the screen, just as this segment with the black ball on the end goes in front of the others. And the striped segment, you're supposed to view as coming behind the screen, just as this red part is behind the screen. If I were to look at the mirror image of this molecule, imagining a mirror is right here, it would look the same, but with the black in the front, the red in the back, but the blue, which is on the left here, would be on the right in the mirror image. And what you can see is that this, as a rigid object, no matter how much I turn it, if I put the black in the front and the red in the back, the blue will be on the left and not on the right. So this molecule is geometrically chiral, and in fact, the molecule is also chemically chiral, because in fact, it's small and it's rigid, and smallness often goes with rigidity in molecules. But not every molecule is rigid. Bigger molecules can be flexible. You can even imagine DNA, which is quite flexible and can tie itself in knots and so on. And even molecules that are not quite so big sometimes have one bond around which a part of the molecule could rotate. And so this definition of geometric chirality isn't going to always be useful when we're looking at molecules. So instead, I want to introduce another definition that comes from the field of math known as topology, which studies flexible shapes, as opposed to geometry, which studies rigid shapes. So an object is said to be topologically chiral if it cannot be deformed to its mirror image, no matter how flexible it is. And on the other hand, if it can be deformed to its mirror image, assuming complete flexibility, we'll say it's topologically achiral. So let's look at an example of this from a molecular point of view. Here on the screen, I have a picture of a molecule which is a pair of linked rings. And I can imagine that by looking at this model of a pair of linked rings. You can see that the molecule on the left and the one on the right are mirror images of each other. And what you can see is that where the one on the left goes in front of another part, like here the green goes in front of the orange, the one on the right, the bottom one, will go behind the top one. And similarly, at the bottom, there's a little tail that sticks out on the left of the bottom ring that says H3C, and on the right, it sticks out on the bottom on the right, and it says CH3. Those are actually the same group of atoms. It's just that they're written like that to indicate that the carbon is the C is where it's attached to the rest of the molecule. So what we can see is that this molecule, the one on the left, can become the one on the right because the bottom ring can turn. And when the bottom ring turns, the part on the left where the green is in front of the orange becomes a part where the green is behind the orange, just as it is in the mirror image. And there's also a pair of hexagons at the top, which we've drawn arrows to indicate that they rotate around the top, so that even though they're slanted left to right in the left image and right to left in the right image, they can turn. And so the molecule can become its mirror image by rotating the bottom ring and rotating the two hexagons at the top. This is an example of a molecule which is chemically achiral because it can chemically change to its mirror image, and it's topologically achiral. But as a rigid geometric object, if we imagine that we can't move either of the rings except for rigidly together, then there's no way that this molecule could turn into its mirror image. So this is an example of where topological achirality describes the chemical behavior better than geometric achirality or geometric chirality. So what's the relationship between these different types of chirality? Well, if an object is topologically chiral, that means even as a flexible object, it's always going to be different from its mirror image. That will actually imply that the molecule must be different from its mirror image, because any motion that a molecule can make doesn't cause one bond to cross through another bond. And so any molecular motion is actually a type of a deformation. So topological chirality is useful in order to know that an object is chemically chiral. In addition to that, if we have a molecule which is chiral because it's rigid, like this tetrahedral molecule that we saw, if you heat it enough, it will in fact change to its mirror form. On the other hand, if we have a molecule whose chirality comes from its topology, meaning there's no way to deform it to its mirror image, then even if we heat it, it won't become its mirror image. So this tells us that topological chirality actually is a more enduring type of chirality that a molecule can have than geometric chirality. So it's useful to chemists from that point of view as well. On the other hand, while proving an object is geometrically chiral only requires that we turn the object and see whether we can get the mirror image or not, proving that a molecule is topologically chiral isn't so easy. For example, I've illustrated a knotted molecule on the screen. If you imagine this knot here representing that molecule, how do I know whether I can get from it to its mirror image by some kind of deformation? Here's its mirror image. We can see that the crossings are exactly the reverse. Here where the orange goes behind, the green goes in front. But no matter how I deform it, I'm not going to be able to get it to look like the green one. But does that mean it can't be done? No, maybe if I kept doing it for 10 more minutes or 10 more years, maybe I would be able to deform it to the other one. So how could we ever prove that one molecule can't be deformed to another? Well, topologists have invented various techniques for this. And one way that we use for knotted molecules and knots in general is polynomials. The idea is that you assign a particular type of polynomial to a molecule or a knot, which has the property that if two knots have different polynomials, it means one can't be deformed to the other. And so in this case, looking at our molecule and its mirror image, where you see that the crossings are reverse of what they are in the original, you see that the polynomial that's assigned to the original blue one is t plus t cubed minus t to the fourth, whereas the one that's assigned to the mirror form is t to the negative 1 plus t to the negative 3 minus t to the negative 4. Because these polynomials are different, it means that there is no deformation from one to the other. So that means that one molecule can't change itself into the other. So this is an example of how topological chirality is useful for molecules and can be shown using a technique developed by topologists. Of course, there are lots of different molecules, and we need lots of different techniques for those to show that they're chiral. And topologists have invented some techniques which are useful, but every day we're learning more and more about topology and developing new techniques which may be useful in the future. Thank you.